You know, life is just a series of choices, right? Some are small, some are huge. But what if for some of the most complex problems out there, the best strategy was just to make the most obvious choice right in front of you and then just repeat? That's the core idea behind what's called the greedy method, and as you're about to find out, it's a really fascinating and sometimes a pretty high-stakes gamble.
So yeah, that really gets to the heart of what we're talking about today. Is the best choice right now really always the best choice overall? I mean, your gut might say no way, but sometimes it actually is. So let's dig in and figure out when that happens and, more importantly, why.
All right, let's really get into it. So the greedy method is this strategy for solving problems where you build up your solution one piece at a time. And at every single step, you just make the choice that looks best in that exact moment. We call this a locally optimal choice, and you're basically just crossing your fingers, hoping that all these right now decisions will magically add up to the best possible overall solution. It feels right, it's super fast, but does it actually work?
To really wrap our heads around the power and the danger of this greedy approach, let's start with a perfect case, a situation where it just works flawlessly. We're going to look at a classic puzzle from computer science known as the activity selection problem.
Okay, so picture this. You're in charge of one single meeting room, and you've got this huge list of people requesting meetings, right? Each one has a start time and an end time. Your goal is simple. Squeeze in the absolute maximum number of meetings you can without any of them overlapping. So, how would you tackle that?
Well, the greedy strategy for this is just beautifully simple. Step 1, you take all those meeting requests and you sort them by their finish time, not their start time, their finish time. Then you just grab the very first activity on that sorted list, the one that finishes the earliest. Once you've said yes to that one, you go through the rest of the list and just toss out any other meetings that would conflict with it. And from there, you just rinse and repeat. Look at what's left, pick the one that finishes earliest, book it, and get rid of the new conflicts. You just keep doing that until you've got no activities left to consider.
And now for the wild part. This super simple, almost naive strategy, it works perfectly. I mean, it's not just a pretty good guess. It is guaranteed to give you the absolute best, most packed schedule possible. It's the optimal solution. Which kind of makes you wonder, right? How does such a simple-minded approach end up with such a perfect result? What's going on here?
Okay, so now it's time to put on our detective hats. We've got this case where being greedy totally pays off, so we have to figure out what's the secret ingredient. What is it about this specific problem that makes our simple strategy completely foolproof?
You know, the whole thing really boils down to this one question. Why is picking the activity that finishes earliest what we'd call a safe move? Why can't we just make that choice, lock it in, and know for sure that we're not going to regret it down the line? There's got to be some kind of special property here that gives us that guarantee.
And it turns out there are. There are two key properties we need to look for. For a greedy algorithm to be provably 100% correct, the problem needs to have something called optimal substructure and, this is the big one, the greedy choice property. And that second one, that's really the secret sauce. Okay, so this greedy choice property, this is the whole shebang. What it means is that you can make that greedy choice, the one that looks best at this very moment, and you can be totally confident that this choice is part of at least one of the best possible overall solutions. You don't need to peek into the future. You just make the choice, commit to it, and then all you have to worry about is the smaller problem that's left over. It's a huge shortcut.
Now, this is something that trips a lot of people up, so let's make it super clear. Both greedy algorithms and another big technique called dynamic programming, they both need that optimal substructure thing. All that means is that an optimal solution to the whole big problem is made up of optimal solutions to its smaller parts. But that greedy choice property, that's the special ingredient for greedy algorithms. It's a way stronger claim. It's saying, hey, this one specific choice I'm making right now is definitely a step in the right direction. Dynamic programming is more cautious. It explores all the choices. The greedy method needs that shortcut to work.
So how in the world do you prove that a problem has this magical property? Well, the go-to technique is something called an exchange argument. You can think of it like a logical stress test to see if our greedy choice is actually safe.
For our activity scheduling problem, the exchange argument goes something like this. Let's say somebody comes along and says, nope, I have a better solution, and it doesn't start with the activity that finishes earliest. We can actually prove them wrong. We just take their so-called better solution, look at the first meeting in their schedule, and we swap it out with our greedy choice, the one that finishes earliest of all. Now, since our choice finishes earlier, there's no way it could cause any new conflicts. So their schedule is still valid, it's just as good, but now it includes our greedy choice. And that right there proves our choice was a safe move from the very beginning.
All right, so we've seen greed come out on top. It feels good, it's fast, it's efficient, but now for the plot twist. Let's take a look at a problem where that same greedy instinct leads us straight into a trap. We're going to dive into the coin change problem.
And this brings us right back to that big question we started with. We proved that one greedy choice was safe, but is that always true? What happens when you just tweak the rules of the game a little bit?
The problem itself sounds pretty simple. You need to make change for some amount using the fewest number of coins you can. And the natural greedy way to do this is to just always grab the biggest coin you can that doesn't push you over the target. For, regular US coins, this strategy works perfectly every time. But what if we use a funky coin system? Let's say we have coins worth 1, 3, and 4, and our target is to make change for 6.
And right here, we see the failure in action. So the greedy algorithm looks at the target, 6, and thinks, okay, the biggest coin I can grab is a 4. So it takes the 4. Now it has 2 left to make. The biggest coin it can take is a 1. So it takes a 1. 1 left. It takes another 1. Boom, 3 coins. But hold on, the best solution was just taking 2 3-cent coins. The greedy choice led us to a worse answer. It failed.
So the really important thing here is to understand why it failed. That first choice, taking the 4-cent coin, it seemed like the best move at the time, but it was a total trap. It led us down a path where we couldn't get the best possible outcome. In other words, for this specific problem, that special greedy choice property, it just doesn't exist. The shortcut isn't safe.
Okay, so now we've kind of seen both sides of the coin, right? We've seen greed win, and we've seen it fail spectacularly. So this brings us to the final verdict. Let's put the fast, sometimes risky greedy approach head-to-head with its more careful, methodical cousin.
Let's really break down the difference here. The greedy method. It makes a choice and it commits. It never looks back. It's incredibly fast, but it's also brittle. It absolutely needs that greedy choice property to be reliable. Now, dynamic programming, that's more like a chess grandmaster. It's always thinking several moves ahead. It explores all the possible choices by solving every little subproblem first. It remembers those answers, and then it uses all that information to figure out the absolute best path to the final solution. Sure, it's slower, it takes up more memory, but it's way more robust, and it can crack those tough problems like our coin example, where the greedy approach just falls flat. So, after all that, what are the key takeaways you should remember? First off, greedy algorithms are amazing, but only when you can actually prove that making the immediate best choice is a safe move. That secret ingredient, the thing that makes it safe, is the greedy choice property. And the tool you use to test for it is that exchange argument we talked about. And hey, if you can't prove it, if the exchange argument doesn't work, that is a massive red flag. It's a sign that you probably need to bring out the big guns, like dynamic programming.
And that kind of leaves us with one last question to chew on. This whole thing isn't just about code and algorithms. It's really about how we solve problems in general. So the next time you're up against a complex choice, ask yourself, is this a situation where I can take the quick, obvious win and be confident it's the right path? Or is this a time where I need to slow down, explore all the options, and be more methodical? Are you going to gamble with greed, or are you going to invest in the careful solution?